Section 9.2, Simplifying Radical Expressions. In Section 9.1, we discussed finding roots of various numbers. In that section, most of the roots we dealt with were perfect roots. In this section, we will start to talk about simplifying roots that are not perfect roots, and also simplifying expressions with variables under the radical sign. Just to review then, one of the problems that we talked about in section 9.1 was the square root of 64. And we had said that the square root of 64 was equal to 8 because 8 times 8 is equal to 64. We also dealt with some cubed roots. We said the cubed root of 8 is equal to 2 because 2 times 2 times 2 is equal to 8. We also talked about some fourth roots. For instance, the fourth root of 256, which we said was equal to 4, because 4 times 4 times 4 times 4 gives you an answer of 256. So, in this particular section, we'll start to talk about what do you do if you have something like the square root of 12. And that's what we will start to explore. So, let's take a look at the square root of 12. In order to simplify this, one of the things that we need to talk about is one of the laws of roots. If I have the square root of 12, if I wanted to, I could break up that 12. 12 is the same thing as 4 times 3. So, both of these expressions, the square root of 12 or the square root of 4 times 3, mean exactly the same thing. If I have the square root of 12, and if I change it to the square root of 4 times 3, now I can take a look at that and I could say, well, I know what the square root of 4 is. The square root of 4 is equal to 2. So I can get rid of that 4. The square root of 4 is equal to 2. I'm going to bring it to the outside, and I'm still left with the square root of 3 underneath the radical sign. So, the square root of 12 can be simplified, and it is equal to 2 times the square root of 3. I want to go through and do the same problem, but I want to do it a slightly different way. I have the square root of 12, and I'm going to rewrite it. Instead of 12, this time, I'm going to say that I have 2 times 6. Now, when I take a look at this, I can't do anything with the square root of 2 because 2 is not a perfect square. I can't do anything with 6 because 6 is not a perfect square. But if I wanted to, I could break up this 6 again. And I could say that I have the square root of 2, that's the original 2 that I started with, and the 6 I could break up as 2 times 3. So I really have the square root of 2 times 2 times 3, which, when you multiply all three of these numbers together, you get that original 12. Well, now, when I have 2 times 2, that 2 times 2 is equal to 4. So the square root of 4 is equal to 2, which I can bring to the outside, and I'm still left with the 3 underneath the radical sign. Because I have 2 2's underneath, what I'm really doing is I'm getting rid of both of them and bringing it out to the outside because I'm looking for the square root of 2 times 2, which is equal to 4. The square root of 4 is equal to this 2. So notice I get the same answer both times. I get 2 square root of 3 and also 2 square root of 3. Certainly doing it this way was a lot faster. And that is what is important when simplifying. The reason that the top way was probably a little bit faster and easier to do is because when I broke down the 12, I broke it down as 4 times 3, and one of the factors was already a perfect square. When I broke it down the second time as 2 times 6, neither 2 or 6 is a perfect square. So, when I go through and I try to simplify these, I'm always trying to find factors of that particular number, and one of them is hopefully a perfect square. Let's take a look at another example. The square root of 32. If I have the square root of 32, I am going to rewrite it, and I'm trying to think of two numbers that I can multiply together to get 32, and one of them needs to be a perfect square. So I'm going to write down the factors of 32. It would be 1 times 32, 2 times 16, 4 times 8. I take a look at all that, and I actually see that I have two of the factors are perfect squares. 16 is a perfect square, and 4 is a perfect square. Well, I want to use the largest perfect square because that means that the other number is going to be broken down a little bit more. So I'm going to rewrite this as 16 times 2. Because the square root of 32 is the same thing as the square root of 16 times 2. Now, I'm going to take the square root of 16. The square root of 16 is equal to 4. So I'm going to get rid of that. I'm going to bring it to the outside, and I'm left with 4 times the square root of 2. I'm not going to do this for all the problems, but I do want to go through and do this problem again. But this time, rather than using 16 times 2, I'm going to use 4 times 8. As soon as I do that now, I see that I have the square root of 4. The square root of 4 is equal to 2. So I could bring that out and I would get 2 times the square root of 8. The only problem with this now is that the square root of 8 can still be simplified because the square root of 8 is equal to the square root of 4 times 2. So, if I rewrite it as 4 times 2 and then take the square root of 4, I would get another 2 that I would bring to the outside. So I would have 2 times 2 on the outside and the square root of 2 on the inside. But 2 times 2 is equal to 4, so I get that final answer of 4 times the square root of 2, which is the same thing I started with, or I had, the first time I did it. It's just that it's a lot easier if you can think of the biggest number that is a factor that is also a perfect square. Let's go through two more examples and then we'll start to move on to something else. I have the square root of 150 and I want to simplify that. So I'm going to start by thinking, boy, what are the factors of 150? 1 times 150. I never really need to write that one out because I'm not going to be able to do anything with that one anyway. But as I go through, 2 times 75 is equal to 150. 3 times 50 gives me 150. 5 times 30 gives me 150. 6 times 25 gives me 150. And 10 times 15 gives me 150. So I'm looking at all of those factors that I have and looking for one that is a perfect square. And I see that 25 is a perfect square, and it happens to be the only one in the list. So I'm going to rewrite the square root of 150 as 6 times 25. Now, I know that the square root of 25 is equal to 5, so I'm going to get rid of it underneath the square root. I'm going to bring it to the outside, and my final answer is 5 times the square root of 6. The square root of 6 can't be simplified at all because the only factors of 6 are 2 times 3, and neither one of those is a perfect square. Here's one more that's very similar. You might want to try this yourself. Turn this off for a moment or so. Try and factor this yourself and then turn this back on again and watch me. Okay, as I go through and do this, I'm trying to think of two numbers that I can multiply together to get 96. I'm not going to write the 1 times the 96 down, but as I think about the factors, 2 times 48 gives me 96, or 3 times 32. So far, I do not have a perfect square. 4 times 24. Oh, there is a perfect square, 4. But remember, I want to have the biggest one. Let's see if there is a larger one. Let's see. Oh, I have 6 times 16 is also equal to 96, and 8 times 12 is equal to 96. I want to use the largest perfect square I have, which is 16. So I'm going to write this as, instead of 96, I'm going to write 6 times 16. And the square root of 16 is equal to 4, which I can then bring to the outside. I do have that negative on the outside, but that square root of 16 is equal to 4, so my final answer is negative 4 square root of 6. In section 9.1, we had talked about simplifying perfect cube roots. And in this section 9.2, we're going to also simplify cubed roots, but they're not going to be perfect cubed roots. And here's an example. The cubed root of 16. So once again now, I'm trying to think of what are two numbers that I can multiply together to give me 16, and now I want one of them to be a perfect cube. Well, if I go through, I can change 16 to 8 times 2. And the cubed root of 8 is equal to 2, because 2 times 2 times 2 gives me an 8. So I can, since this is a cubed root, I can bring out that 8. The cubed root of 8 is equal to 2. So my final answer is 2 times the cubed root of 2. This is where that one piece of paper that I gave you in class, which was the reference sheet for 9.1, 9.2, and 10.3, might come in handy. So before continuing, I've written down some of the perfect cubes that are on that reference sheet over here on the right-hand side. So that might come in handy, as I said. Let's see if we can figure out what is the cubed root of 250. I'm trying to think of two numbers I can multiply together to get 250, and hopefully one of the numbers that I'm going to choose is one of these numbers. And as I take a look at that, I could rewrite 250 as 125 times 2. And now I can go through and I can figure out, well, what is the cubed root of 125? The cubed root of 125 would be equal to 5. So I can get rid of the cubed root of 125, bring a 5 to the outside, and I am left with 5 times the cubed root of 2 for an answer. And here's one more example. How about the cubed root of negative 135? Once again, I'm taking a look at the list I have over on the right in green, and I'm trying to think of, boy, what are two numbers I can multiply together to get 135? I'm looking at those and I'm not really sure, but I do know that 135, ending in a 5, a factor of it would be 5. So I know that 5 times something has to equal negative 135, and when I go through and do the math, I'm going to get 5 times 27, and I'm going to make that a negative 27 because I need a negative 135. So I have changed the cubed root of negative 135 to the cubed root of 5 times a negative 27. Now I need the cubed root of negative 27. The cubed root of negative 27 is negative 3, because negative 3 times negative 3 times negative 3 gives me a negative 27. I can bring out that negative 3, and I'm going to be left with the cubed root of 5. So the final answer is negative 3 times the cubed root of 5. We can, of course, simplify fourth roots, just like we can simplify square roots and cubed roots, and here's an example. Let's simplify the fourth root of 32. I'm trying to think of two numbers I can multiply together to get 32, and hopefully one of them is a perfect fourth root. And right now I'm circling in green all those numbers. This is from your reference sheet. And I see that I could rewrite 32 as the factors 16 times 2. So I'm going to rewrite 32 as 16 times 2. the fourth root of 16 is equal to 2. So I can bring out the 16. I'm still going to be left with the fourth root of 2. So my final answer is 2 times the fourth root of 2. I want to talk about this same problem again one other way. Let's say that you were doing this problem with the fourth root of 32. You're trying to think of two factors of 32, and the only ones that you really come up with are 4 times 8. Well, you can do this problem exactly the same way. I get the fourth root of 4 times 8, and now what I need to do is I need to go through and I need to factor down each one of these numbers. The 4 could be factored down as 2 times 2. And the 8 could be factored down first as 4 times 2, but also 2 times 2 times 2. If you multiply 2 times 2 times 2 times 2 times 2, I'm going to get that 32. So, if I wanted to, I could rewrite it this particular way, the fourth root of 2 times 2 times 2 times 2 times 2. Now, if I group together 4 of these, 2 to the fourth power is really what I have. And the fourth root of 2 to the fourth power is just equal to 2. So I can cross out all 4 of those 2's, and I'm going to get 2 the fourth root of 2, which is the same answer I have up here. It was just a lot faster, a lot easier since I came up with two numbers to equal 32, and one of them was a perfect fourth root. Here's one more example. And once again, if you want to turn this off and try and work through this yourself and then turn this back on, you might find that a good way to go through and do this. Okay, hopefully you've had a chance to take a look at this. I have the fourth root of 128. I'm trying to think of two numbers that I can multiply together to get 128, with one of them being a perfect fourth root. Well, I'm taking a look at these, and there's no way it could be 625. There's no way it could be 256, because those are not going to be factors of 128 because they're larger than 128. So then I'm thinking about 81. Is 81 times something equal to 128? No, it isn't, so I know it can't be that. So it needs to be 16 times something. And if you go through, 16 times 8 does give you 128. So I'm going to rewrite this. Instead of 128, I'm going to rewrite that as the fourth root of 16 times 8. And then, as I go through, the fourth root of 16 is equal to 2. So I can get rid of the 16. I'm going to bring it to the outside. I am going to be left with 2 times the fourth root of 8 for my final answer. Section 9.2 has a lot of information in it, and this video is already long enough. So I'm going to stop here and start up a new video that I will call Section 9.2 Part 2. As always, if you have any questions over this material, or if I could help you in any way, please let me know.